Now let's go ahead and take a look at something in context. A standard 8x8 chessboard contains 64 squares. We know that, right? 8 rows of 8 columns would be 64 individual squares. Actually, this is just the number of unit squares, right? The 1x1 squares. How many squares of all sizes are there on a chessboard? Start with smaller boards, 1x1, 2x2, 3x3, etc. Find a formula for the total number of squares in an n×n board. Okay, so first of all, let's think in terms of sequence. If n represents the dimension of a square board, so 1x1, 2x2, etc., then a sub n will represent the total number of squares of all sizes that we can create for that board. So let's look at an example. 1x1. All right, well, 1x1, there's 1 unit square, and overall that's just 1 square. So there's only 1 square you could possibly form out of a 1x1. Not very interesting. For n equals 2, now we would have a 2x2, and let's think about this. We have a 2x2, which already has 4 squares, just by the fact that we can count them. But then you could also form a 5th square, which would be the entire 2x2 itself, right? So you have these 4 smaller squares, and then you have this 1 larger square. You can't have a rectangle. It can't be like one of these dominoes because that's not a square, that's a rectangle. All right, so that means we have 5 different squares. Again, 1, 2, 3, 4, and then 1 big square. Now let's look at a 3x3. That's where things begin to get a little bit more interesting. And so we'll draw a 3x3. We know this already has 9 squares. And then it's going to have anything that's a 2x2 is also a square, right? So I have 9 squares individually. Then I have this square right here. So I can take that. That's a square. Then I can shift that down 1 row, and I get another square right here. Okay, so that's already 11 squares that we can form. And then, of course, I can do the same thing over here. If I just shift this green square to the right 1 column, then I have a square there. So that's 12. Also, I can shift that one down. That's 13. And then I have the big square all the way around, right? So there's 14 squares that I could form out of that. Now that you can see how complicated this can start getting, because writing a function for this is difficult without having some numerical data to use. Let's do one more, and then we could start to analyze whether or not we have, whether this is a delta k constant sequence. So for a 4x4, just divide in half and then divide in half again to get our 4 columns. Divide in half again. So we have 16 individual, and I'll just kind of keep tabs down here. Then we can have this square just like we did with the 3x3. There's plus 1 more, so there's 17. Shift that down 1 row, there's 18. Shift that down 1 more row, there's 19. Okay, now I could, so that means within each column I could have 3 2x2s. So I'll just say plus 3 there. Now imagine that we take this entire thing and we just shift it over 1 square. So now we're focusing on the middle stack. And again, we'll have 1, 2, 3. So we'll have 3 more there. And then we can take that entire thing and shift it over 1 square. And then we'll have 3 more here. 1, 2, 3. All right, now we can also have 3x3s inside of a 4x4. So you can see this gets a little bit more elaborate. So let's see how many 3x3s I have in this 4x4. Here's 1, starting at the top left corner. Now I can shift that down 1 row, and there's a second one. And now, well, okay, I can shift that 3x3 over 1 layer. over one column, and then I can repeat the same thing, and I'll get two more 3x3s, namely this one and this one. That's all the 3x3s I could have in there. Now I have also the big outer one, the 4x4. So that's yet another way I could form a square of any size out of this. So we get plus one more. Now let's count this all up. So we have 16 plus 9 is 25, 27, 29. We have 30. 30 squares inside of a 4x4 of all sizes. Okay, I think we have enough data to at least check our differences. Now, I already see that the differences are not constant. So if I analyze 1, 5, 14, 30, I look at the differences, 4, 9, 16. If I look at those, I get 5 and 7. Okay, those aren't constant yet, which means that I need to look at a 5x5, because if I do the third difference, I can't see if the third differences are constant because there's only one of them. So if I had another value right here, and I could get a difference there, then I could look at the difference between those two and look at the difference between these two, and as long as I get a 2 there as well, then I'd be good. But the problem is I need that fifth value. So let's look at a 5x5 and see if we can sort of expedite this. 2, 3, 4, 5. 2, 3, 4, 5. So I have 25 squares. Then as far as 2x2s, let's use the same kind of logic. I could have a 2x2 here, and then I could shift it down to a second one, shift it down to a third one, shift it down to a fourth one. So there's going to be 4 of them here for these 2 columns, then I'll have 4 more here for these 2 columns, then I'll have 4 more for these 2, and 4 more for these 2. So that's going to give me 4 plus 4 plus 4 plus 4 is 16. 16 2x2s. Now I move on to 3x3s. Okay, so for 3x3s, I'll have, let me do some different color. I have a 3x3 here, and we can shift that down twice. There's a 3x3, and there's a 3x3. So I have 3 3x3s in that column. Now if I look at these 3 columns, I'll have 3 more. And then if I look at these 3 columns, I'll have 3 more. So that gives me a total of 9 3x3s. And now I have to look at 4x4s. Well, if you haven't noticed, then as we go higher, as we go one for a 4x4, when we looked at a 3x3, there were 4 of them, and that's going to be because with 4x4s we can only shift down one time before we bottom out. So here's a 1, 2, 3, 4. There's a 4x4, and then I can get another 4x4 if I shift that down. So that's going to give 5x4s, and then if I take everything and just shift it over to these 4 columns, I'll get 4 more. So you see we also get 4 of the just smaller size than the 4x4s than in the 5x5 that we're in. And then how many 5x5s? Well, there's just 1. So if you can see that here we had 16 plus 9 plus 1. So 16 plus 9 plus 4 plus 1. Here we have 25 plus 16 plus 9 plus 4 plus 1. Here we had, what did we have? We didn't keep track of all that. We had 9 plus 4 plus 1, and that's 14. And here we just had 4 plus 1, which is 5, and here we just had 1. So it seems like we're always adding on a quadratic of the value of n that we have in our problem. Okay, almost done. So add all these up. That's going to give us the total number of squares we could form. And here we have, okay, that's just going to be 30 plus 25, which is 55. So back over here, now 55, the difference from 30 to 55 is 25. The difference between 16 and 25 is 9. And check it out, we get a constant third difference of 2, which means that we have a delta k constant polynomial. And in our similar vein, we could take our data here, now that we have 5 data points, and we could enter them just like this. We're going to start with n equals 1, and let's go ahead and do that in our table. Now in Desmos, I just chose to relabel the column to make it n1, just makes it, I don't know, maybe a little bit more consistent with what we're writing down on our page. And so I just typed in n1, and here I typed in an. So I'll just have to refer to them as n. We could even just use n if we wanted to, I think. As long as it's not x, you could use n. Let's take that away. There, okay, so n would work as well. And that way we wouldn't have to do the n1. So let's take that away. So you can see here what I'm going to do. Let's take away all those n1s. All right. So yes, we get a perfect cubic fit here, an. Now here I can use a because that's not going to be confused by an. A, B, C, and D is what I'm calling my coefficients. Then I'm referencing the column that has the quantity n. Now here we have our parameters, and if you notice, they get rounded. It's ideal to figure out what these fractional values are, and maybe Desmos isn't the best tool for this because it will round off. Now 0.33 repeating is going to be 1/3. Here we'll have 1/2, and 0.167 I believe is 1/6. Take 1 divided by 6, yeah. So this is a 1/6. Excellent. Here I have my solved recurrence relation by using polynomial fitting on the data. So this exercise I really like because it goes through the thinking process of setting something up, but then we also have the mathematical component of then, okay, well, how do we know how many squares a 6x6 had in it without having to go through and actually do all of the counting? So we had to do a little bit of work to get there. We kind of had to go up to the n equals 5. Otherwise, we wouldn't be able to see the third difference and to see that it is indeed constant.